So in our last discussion, we derived the one locus two allele model for viability selection. And I said that for those people who are not very comfortable with maths, who are not able to follow some of the calculus concepts or some of the probability concepts, for them I am going to repeat the primary messages from that derivation, and this lecture is where we are going to do that. So for all those people who were able to follow the maths and who understood what was happening, my apologies, but I would still recommend that you go through with the contents of this lecture, because right towards the end there will be one or two things extra that were not discussed in the previous case. Also, it's always a good idea to repeat your understanding a few times, because then that's what gets stuck in your brain. So anyway, without further ado, so we are looking at certain features of selection, primarily from the insights that are coming from theoretical modeling. So in the last class, we saw that the average genotypic fitness is given as W bar equal to P square W11 plus 2PQ W12 plus Q square W22, where P is the frequency of allele A1, Q equal to 1 minus P is the frequency of allele A2, and W11, W12 and W22 are the genotypic fitnesses. So we explicitly talked about the viability selection case, which means that W11, W12 and W22, they represented the survivorship of the genotypes. Then we said that assuming that these three things W11, 12 and 22 are constants, we said that delta P will be equal to PQ by 2 W bar dW bar dP, where dW bar dP gives me the way W bar is changing with change in the allele frequency P. And I said that this is a very famous equation named after the great population geneticist Sewell Wright, and it's called the equation for fitness landscape, or also known as the equation for adaptive landscape. And as I said, this is when the survivorships are constant. When the survivorships are frequency dependent, that is, the survivorship values change with the frequency of each genotype, then we get an extra term over here, this term, and there is a minus expectation of dW dP that enters into the picture. Now, what are the implications of this? The main message that I want to give you in this context is that in the frequency independent case, you can understand the dynamics of selection, how P is changing, simply by studying how W bar is changing with P. Okay, the entire evolutionary dynamics can be understood in this context. So I am showing you a graph of W bar against P. Now here you can see that this is P equal to 0, this is P equal to 1 over here. Now what happens when P is equal to 0? That means there is no allele A1 in the population, which means all individuals are A2A2. Now if all individuals are A2A2, then what is the average fitness of the population? The average fitness of the population is going to be the genotypic fitness of the A2A2 genotype, which is W22. So at this end of the graph, you are going to have, when P equal to 0, W bar is equal to W22. What happens at the other end of the graph? When this equal to 1, P equal to 1, that means that you only have A1 allele in the population. When you only have the A1 allele in the population, that means all individual genotypes are A1, which means that the average genotypic fitness is going to be W bar equal to W11, right? So these 2 points at the two ends, P equal to 0 and P equal to 1, these 2 points are fixed at W22 and W11 respectively. Now the rest of the function, how W bar changes with P, is going to be between these two extreme points, and the steeper the slope of W bar, the faster will allele frequency change. Okay, that's the main thing over here, and the faster the population is going to evolve. Now obviously if the this vertical distance, that is the distance between W11 and W22, this distance is very large, then the chances that this graph is going to be steeper at some point is much larger. So roughly speaking, that is why if you have this distance to be large, then the chances that at least during some part evolution is going to be very fast, that chance goes up. Now, with this information in our head, we are now going to look at the 3 points that we had figured out when we were playing with the simulations. So, this was the lecture before the previous one. So, the first point that we saw was when the survivorship are close to each other, when the genotypic fitnesses are close to each other, selection is slow in changing the frequencies. When they are very different, the change in frequencies is fast. Okay. Now, to explain that, we will quickly go to Excel. Okay. So, let us assume that our starting frequency, we are keeping it at 0.1, and let us say we are now going to have these very different from each other, say 0.9, 0.7 and say 0.1, right. So, what I have done over here is I have the change in allele frequency over time. This graph we had already seen. I have added an extra graph over here. What graph is this? Here I am putting the frequency of A1 P on x axis and I am plotting the average fitness W bar on y axis. Where am I getting this graph from? I am getting this graph from this stuff over here. So, what I have done is here I have taken P equal to 0, 0.01. So, at step size of 0.01 I have increased it all the way up to 1. Then I have taken Q 1 minus P and I have just put them over here, and then this column I have put the formula of W bar, which is that P square W11 plus 2PQ W12 plus Q square W22. Where am I getting the values of W11, 12, 22? I am picking them up from here. So, if we change stuff over here, we can see the effect of that in this graph. Now, one quick thing to note is that here I have time on x axis, here I have frequency of A1 on x axis. So, that is why if I change the P value over here, things will change in the left graph, but it will not change in the right graph. Why? Because in the right graph I have already hard coded the values of P, that is the frequency of A1, right. So, that is something that you have to keep in mind when you are looking at these two graphs. Now, look at what I have put over here. Remember I said that this side is going to be W22 and this side is going to be W11. I am sorry, not on this graph. On this graph, this side is going to be W22. So, this is 0.1, that is why I have 0.1 over here. This side is going to be W11. So, you can see this is 0.9, I have 0.9 over here, and the rest of it is just going to, the rest of the line is just going to connect these 2 points. Now, obviously, the greater the difference, the more will be the difference between this and this, the vertical distance, and therefore, more is the chance of getting a higher slope, which means that the change in allele frequency when the slope is high is going to be greater. Okay, delta P will be greater, and more importantly, what we saw in the simulation was that the sign of delta P will be the same as the sign of dW bar dP. So, in this particular case, you can see that the slope of the graph is always positive, and therefore, delta P will always be positive, which means delta P will increase in this direction, which means frequency of A1 will keep on going up, and that is precisely what you see over here. Now, you make these points come much closer to each other. So, let us say I make this as 0.85 and I make this as say 0.8, and what do you see? You see that starting from the same start point P0 equal to 0.2, this is taking much longer to hit the frequency of 1, and you can see over here that the slope has become much shallower. Okay, it has become much flatter. So, this tells you that the greater is the difference in the relative frequencies, the faster things will happen, and vice versa. Okay, so that explains our point 1, and now we go back to our PowerPoint. Where is it? Yeah, okay. So, what was our second point? We saw that sometimes one of the alleles was getting fixed. In fact, most of the times one of the alleles was getting fixed, However, there are certain situations where both alleles were present in the population, and also we saw that in terms of what is happening in the long term outcome, the equilibrium, sometimes the allele frequencies are mattering and sometimes the allele frequencies were not mattering. So, what was going on? So, again going back to our Excel, what happens is like this. Suppose we have a situation which is, let us say, like this, where you have both the homozygotes having lesser fitness than the heterozygote. When you have a scenario like this, then every case your equilibrium frequency is much lower than 1. It will be, sorry, not much lower, it will be somewhere between 0 and 1. Okay. So, when that happens, this relationship between W bar and P, that takes some kind of a convex shape with a maxima somewhere in the middle. Okay. Whenever you see this thing, this is when you know that the equilibrium frequency is going to be somewhere between 0 and 1. Now, what is the implication of this? The implication of this is that at equilibrium, both A1 and A2, both alleles are going to be there in the population. Okay. Till now, all the cases we were seeing, one allele was going to fixation, the other allele was going to extinction, right. This is the situation where that will not happen. Now, if you have a situation like this, does the initial allele frequency matter? Now, you can satisfy yourself that it actually does not. I can put whatever value I want over here, the equilibrium frequency is always going to be the same. Now, this was the situation where, as I said, the heterozygote is fitter than both homozygotes. This is what is technically known as overdominance. But we have another scenario where the heterozygote is less fit than the two homozygotes. So, let me just do that. So, let us assume that this is 0.9 and let us assume that this is 0.8 and let us assume that this is whatever 4 say. Okay. Now, if you have a scenario like this, look at the shape of the W bar graph. This has now become concave. Now, it has become concave means that there is going to be a minima somewhere in the middle, okay, somewhere about here. Now, if you see the graph like this, you immediately know that now one of the two alleles is still going to go to fixation, but which one it will be depends on where your system is. So, think about it. Here you see that the minima is somewhere between 0.4 to 0.5. Okay, we can figure out the precise value, but it is somewhere over here, right. Now, the system, the frequency of allele A1 on right hand side will go up like this and on the left hand side it will go like this. In both situations, W bar, the average genotypic fitness, is going up, but in one case allele A1 is going extinct, the other case the allele A2 is going extinct. Okay. And just to show you in the simulation, so here if we look at it, our equilibrium point is somewhere between 0.4 and 0.5. So, we took our P0 as 0.3, which was to the left of this, and therefore, it went in this direction. So, if what I said is correct, if I take it greater than 0.5 or 0.45, then I should have the opposite of this. In other words, A1 should go, P should go to 1. So, let me make this 0.8 and there you go. Okay. So, sometimes you get low, fixation of allele A1, sometimes you get the fixation of allele A2. So, let me just play with this a little more time, few more times. So, just to show I am doing it as 0.2, which means I am putting it over here. So, what should happen? P should go to 0. Does that happen? Yes, it does. Let me put it, let us say 0.75 or let me make it 0.55, okay, a little larger. Let us see what happens. Okay, 0.55 it goes to 1. You can see it is going in the other direction. So, if I were to summarize the whole thing, this is what the summary looks like. if I have a scenario where the fitnesses of the 3 genotypes are going monotonically, in the sense that W11 is greater than W12 is greater than W22, or the other way around, W11 is less than W12 is less than W22. In that case, the consequence for allelic frequency at equilibrium is fixation. One or the other allele is going to go equal to 1, frequency is going to go equal to 1. The allelic frequency, the starting allelic frequency will not matter at all, and which allele will get fixed will depend on whether W11 is greater than W22. If so, A1 will be fixed. If W11 is less than W22, A2 will be fixed. If you have a scenario where W12 is greater than both W11 and W22, heterozygote is superior to both homozygotes, we call it overdominance, and in this case the polymorphism will be maintained, which means at equilibrium both alleles are going to be there in the population, and again in this case it does not really matter where you start your allelic frequency from. In the case where the heterozygote is less fit than both homozygotes, there you are going to have unstable polymorphism, which means that there will be one single point. Somehow if the population reaches there, it might remain stable for some time, but if there is even a little bit of a perturbation, then it will fix for one or the other allele. And if in general, if you are having no noise or anything, the starting frequency will matter in this case in a simulation. So when you start to the left, then allele left of the equilibrium point, unstable equilibrium point, then allele A2 is going to get fixed. When you start to the right, allele A1 will get fixed, and this is what is called as underdominance. Now, why am I making such a big point out of this? This will become clear in one of our later discussions, but realize one thing over here. Normally we say that selection reduces the variation in a population, but that is not what is happening in the middle case. Okay, you can see that there is a situation where even though there is selection, you are going to have both alleles maintained in the population, and this happens when a particular combination of genotypic fitnesses are realized, basically when the heterozygote is superior compared to both homozygotes. Okay. Remember, everything that we discussed till now is true when the genotypic fitnesses are constants. They do not change based on the genotypic frequencies themselves. What happens if that is not true? That is when you get frequency dependence of genotypic fitnesses. Okay. If that happens, as we saw in the discussion yesterday, in our last discussion, all kinds of dynamics of P become possible. Okay, you can have the kind of dynamics that we saw for the density independent, for the frequency independent case. You can even see situations where the dynamics of P becomes totally chaotic, and here chaotic is a technical term which means that it never repeats itself. Okay, and what kind of dynamics you will end up getting will depend crucially on precisely how the genotypic fitnesses are dependent on the genotypic frequencies. Okay, you have one relationship, you get chaos, you have another relationship, you will get some nice monotonic kind of stuff, and so on. So just to give you one random example, here is the situation where under a certain kind of frequency dependent selection, this is what is happening to the change in P, with over time. As you can see, it is not settling down, and it is not that this is a transient phase or anything. I can simulate it for thousands of generations. It will always oscillate, very chaotically like this. And if you look at the corresponding figure for the W bar versus P graph, you can see that it is a very complicated figure. Okay, you can straight away see that you have one minima over here, another minima over here, one maxima over here, and so on. Okay, so the basic message I am trying to give you over here is that the moment genotypic fitness becomes frequency dependent, the predictability of the dynamics becomes much less, and it all becomes very, very context dependent. Now, what are the implications of this? So, what I will give you is the implications in detail. This is kind of a summary of whatever we have discussed till now, And once I am done with the detailed discussion, I will give you a one sentence implication of the whole thing. So, when the genotypic fitnesses are constant, frequency independent, then average population fitness will always increase irrespective of the starting allele frequency. Okay. This is what leads to the common notion in the minds of most people that selection increases the fitness of the population all the time. That is coming out of this derivation. Okay. However, as I showed you, that the moment you go from frequency independent to frequency dependent, this relationship will break down. Some cases fitness will still increase due to selection, average fitness, but in many cases average fitness will actually go down due to selection. Okay. And in many cases you won't even be able to predict. Okay, it will move around very unpredictably. And the special case where due to selection average fitness of the population can go down, that case is what is known as Darwinian extinction, also known as evolutionary suicide. Unfortunately, I did not find a very good example of a real life example of evolutionary suicide in the literature. However, as far as the theory is concerned, it has been studied very nicely, and people have shown that under many conditions a population can actually go down that path and commit evolutionary suicide. Now, everything that we said till now is if you think of selection in terms of viability, in terms of survivorship. But remember, even Darwin himself, when he composed the thing, he talked about some genotypes leaving more babies than others. And when we were deriving the Hardy-Weinberg, we explicitly said that you can have selection in terms of fertility and you can have selection in terms of viability. If you think in terms of fertility, then actually that entire process becomes way more complicated. Okay. And for example, one of the things that can come out from a fertility selection scenario is that the allele frequencies can become constant across generation, and yet the genotypic frequencies can keep on changing. Okay, just think about that. That is something that doesn't happen in the viability selection model. Okay, that is why we were looking at only the allele frequency going constant, and when that happened we said okay, population has reached equilibrium. But in this particular case, you can have equilibrium in terms of allele frequency, but you can not have equilibrium in terms of genotypic frequency. Okay. This is something to which we will come back. This particular phenomena can happen in another scenario. This is important because lots of time you will see that evolution is simply defined as change in allele frequency. Okay, many books actually do that. And that is something that lots of modern evolutionary biologists are taking grave objection to. And that is why I am explicitly showing you cases where allele frequency change doesn't necessarily mean genotype frequency change, or doesn't necessarily mean, where allele frequency changing doesn't necessarily lead to genotypic frequency changing, or the other way around. Genotypic frequency changing doesn't necessarily lead to allele frequency changing. Therefore, when you are talking about evolution, you should be very careful and state, are you talking in terms of the allelic level or you are talking in terms of the genotype level. Okay, this is again something that is not really there in the literature, but not really there in the textbooks, but if you look at the literature, then people are becoming very conscious of this particular thing. And everything that we said till this point is when we are thinking about selection acting alone. But in any real life scenario, selection is not acting alone. Selection is acting in conjunction with a bunch of other evolutionary forces, for example mutation, for example genetic drift, about which we will be talking at some point in the next module. And this selection, the way it operates is very much dependent on, or rather the dynamics that it leads to is very much dependent on the genetics of the whole thing. Okay, whether the alleles that are being considered, are they dominant or are they recessive, or are they dominant to different degrees, all that changes the way the dynamics proceeds. And also a huge elephant in the room is what is known as the transmission fidelity. Now, if you are talking in terms of alleles, then barring mutation, an allele is passed faithfully from a parent to an offspring, barring mutation. But if you are talking in terms of traits, remember everything that we are talking about, we can also think in terms of traits. If you are thinking in terms of traits, then traits are not passed as it is from the parent to the offspring. Traits are passed to various degrees. Some traits are passed very faithfully, some traits are passed less faithfully, and one can show that the effect of selection is very crucially dependent on the transmission fidelity of the trait being considered. If the transmission fidelity is very high, then it is relatively easy to model that thing. If the transmission fidelity is not very high, then modeling the effect of selection becomes a very big pain all over the body. So, the simple point that I am trying to make is that although conceptually selection is a very simple thing, okay, 3 conditions being met, selection will happen. And when selection happens, in most of the cases, unless you are at an equilibrium or something, frequencies of the trait or frequency of the allele, all those are going to change. All that is fine. Darwin said it in just a few words. However, when you actually look into the biology of the system and you are trying to figure out, what will this lead to, what will be the effect of selection and other forces on the evolutionary trajectory, then it becomes pretty complicated in most of the cases to predict it. And whether you see that complication as a mess or whether you see that as a challenge to grapple with, to figure out, that is what distinguishes you as a non-evolutionary biologist, if you see it as a mess, versus something interesting, something superb if you are an evolutionary biologist. Okay? And the people who are doing it, well, there are many people who are studying this problem in great detail. The population geneticists are obviously studying this in great detail. The quantitative genetics people have a lot to say on this, and experimentally the class of people who are studying this problem are the evolutionary ecologists to some extent, and more importantly the experimental evolutionary biologists or the experimental evolutionists, who have this is their bread and butter basically. These are the kind of problems that they study, that if selection is interacting in different ways with different evolutionary forces, what exactly is it leading to? Now, obviously this is complex, but the course of which you and I are a part, that's an introduction course. Okay. So, as far as we are concerned, we are not going to get into all those complexities. Okay. We will keep things simple. We will by and large deal with those examples where selection increases the average fitness or some kind of a measure of fitness and so on. These are the examples that you are typically going to get in most textbooks. Safe area, that's where we will mostly hover from this point onwards. However, I want you to keep in mind while you are reading all those simple examples and those simple things, that all this is just a prelude, just an introductory note for some process which is way more beautiful, way more complex, way more magnificent. And if you forget all the maths that I did in the last discussion and all the graphs and all the slopes and this and that, all those relationships, if you forget all those stuffs and you remember just this one thing, that although simple, the effect of selection can be complicated, my job in last lecture and this lecture is actually done. Okay. So, in the next discussion, we are going to look at certain other features of selection, but instead of looking at it from the mathematical point of view, from models etc., we are going to bring in more experimental insights. Okay. See you in the next discussion.